All right, so welcome everyone. Good day. Welcome to YSIMS Academy. We're going to continue from where we stopped, but still on the Aspen HiSys simulation training. And then we are going to be looking at module 3.2, which is under module 3, which is the process modeling and unit operation. All right, so basically we're going to be talking about gas gathering in this module 3.2. And gas gathering, basically, it's all about moving gases from different wells across a very vast distance, not just very vast, but across a distance to a particular location. All right. So basically, we are looking at this example here. Okay, in this example, IC steady state capabilities are used to mimic a gas gathering system situated on a variety of terrain. The actual setup of this system is depicted in the following figure, which I'll be showing to you shortly, which is a topographic map overlay. All right. So 4 wells spread across an area of around 2.0 square kilometer make up the system, which is connected to a gas plant by a series of pipelines. All right. So we're going to be transporting the gas from different wells through pipes to the gas plant. All right. So this is the topographic map, and then this is well A, well B, well C, and well D. Now just picture this as coming from different locations. Imagine this is coming from Delta State, this is coming from Port Harcourt, this is coming from Benin, and this is coming from Bayelsa. All right. So we can actually see that they are going to Lagos for treatment. It's possible. All right. So or if you are outside the country, maybe in the United States, you can see that this is coming from Texas, this is coming from Pennsylvania, this is coming from Louisiana, this is coming from Oklahoma, and then they are all going to West Virginia. So it all depends on how you look at it. So basically, this is actually a practical problem that we could actually simulate. This is a real life hands-on experience that we can actually simulate. All right, so you knowing this will help you wherever you're going to be working, and then maybe they decide to have a gas transportation system, and then you can help them do that. All right, so this is the components we're going to be working with. We have methane, ethane, propane, iButane, N-butane, I-pentane, N-pentane, N-hexane, and then we have a C plus, C7 plus, which is a hypothetical component. We have nitrogen, we have CO2 and H2S. All right, so let us start the process. Let me bring up my ISIS. Sorry. Okay. All right, so now let's add our components. All right, so we're going to be starting from methane down to N-hexane, and add all this. Then we need to add our hypothetical components. All right, so instead of a batch hypo, we are going to be using just to create one, and then using the new instead of group, so new hypo. All right, so change this to C7 plus. All right, and then the molecular weight was given. The molecular weight was given as 122, so change this to 122, and then the liquid density was given as 47.45. 47.45. That's in pounds per cubic feet. All right, so we estimate the remaining ones. We don't have the remaining ones, it wasn't given, so we just estimate it, and then we have results for them. So the next thing we just need to do is to add it to the list, and then change this back to pure components and add the remaining things. We have nitrogen, we have CO2, is nitrogen, CO2, and H2S. All right, CO2 and H2S. All right. So our fluid package is the Penn Robinson. So we're going to put it on the Penn Robinson. Remember, working with natural gas, so it's okay. And then we go to the simulation environment. All right, so we have 4 streams. So 1, 2, 3, and 4. So they are all representing the wells. So this is going to be gas well 1. Let me start. Gas well 1. Okay, let's see the parameters for this. Okay, we have a temperature of 40. We have a pressure of 4,135. So let me do that. Temperature of 40, pressure of 4,135. Yeah. All right. And then the flow rate, the mole flow is, remember, if you look at this, we have kg mole per hour, so that's the mole flow rate is 425. All right. So 425. All right. So now let's go to composition, and then we add the compositions for this. Okay. All right. So we have the compositions here. Let me move it to here. Should be able to see better. Okay. All right, so let me add the compositions. We have 0.6230. Okay. 0.28. We have 0.0163. 0.00433. 0.00821. 0.00416. 0.00405. 0.00659. 0.00992. 0.00554. 0.00225. 0.0154. All right, so after adding all this, you can see that it's equated to 1. If you remember very well, when we talked about the mole fractions and the mass fractions, we see that every component added in that particular list should be equal to 1. So we are saying that we have 0. That's like 62% of methane, we have 28% of methane, and the likes of that down. So we see that everything is equal to 1. We just click on OK, and then our gas well 1 is ready. All right, so let's define gas well 2. Gas well 2. Okay. For gas well 2, we have the temperature as 45. We have the pressure as 3450, and then the mole flow is 375. All right. Okay, so we go to the composition. And then all of them, let me bring this back in. All right, so we can see that the composition. All right, so the composition for the 4 wells are the same. All right, so let me show you how to do this. So we don't need to specify the compositions again. All we just need to do is why it's very simple. You come to define from stream. All right, so I'll take out this temperature, take out this pressure, take out the flow here, and then the colorations and all that, and just leave it on composition. So we're going to be defining the stream from, that's the composition from gas well 1. So what this does for us is takes the composition from gas well 1, and then you can just automatically add it to this stream. So I click on OK, and you see that it's solved already. All right, so let's go to gas well 3. All right, gas well 3. All right, so let's check our. All right, so let's define that of gas well 3, and then bring this up as for gas well 3. Okay, we're just giving the temperature and then the flow rate. So temperature is 45 and then the flow rate is 575. All right, so let's just define this. That's 45, 575. Yes, 45, 575. All right, so all right, so the temperature, the pressure wasn't given, and then the composition. So I'm just going to be defining this from stream 1. I'm going to be defining this from stream 1. So we're going to be defining the pressure and the composition from gas well 1. And then I think that's okay. And let's define for gas well 4. All right. Gas well 4. Let's see. The temperature was 35 and then the mole flow is 575. So I'm going to be defining the pressure from gas well 2. So let's just do this. So 35, 545. So 35, 545. All right, so we define from gas well 2. Okay. All right. So that is ready. So the next thing to do now is to add our pipes. So let's start with the first one, branch 1. Let me open this up for you. Let's work with this. So starting from here, well A, that's gas well 1. We're having branch 1. So this is it. This whole line here is the branch 1. And then this circle represents the segment. All right, so let's do that. Let's open this up. Now we look for pipe segment. This is pipe segment. Select pipe segment and then we drop it in. Okay, so I'm going to say my gas well 1, my outlet is going to be B1 out. Okay, that's branch 1 out. Remember, this is branch 1. So branch 1, and then the energy stream here, I can say B1 here. All right, so it's asking for segments. Say no segments added, so we need to append the segment. So all you just need to do is to come to ratings, and then you see append segment, click on append segment. All right, so now let's check what we have for this pipe segment. All right, so this is the information we're going to be using for my pipe segment. All right, so this is the information we're using for it. We have the branch 1, branch 2, accordingly the way it is listed. All right, so branch 1, we have 3 segments. We have segment 1, segment 2, and segment 3. All right, so we have to append 3 segments to it here. We have 1, 2, and 3. All right, so the length of the first one is 150, and then the elevation change is 6. All right, so let's do this as the length 150 meters, elevation change is 6 meters. So it's giving here. All right, so moving on, now we need to specify the outer and inner diameters of the pipe. So what we just need to do is to come to view segment. All right, let me show you so that you understand. Okay, so we have pipe branch, we have the diameter, so we're going to be using 76.2 as diameter, and then from here we see that every branch is buried at a depth of 1 meter and scheduled 40 steel pipes are used throughout. Understand? So we're going to be selecting schedule 40. That's the pipe schedule. Schedule 40. We look for 76, but approximately we don't have 76 here, so we approximately will make use of 80 millimeters. All right. So with that, we click also. It's to help you with the outer and inner diameter. Now we need to do that for segment 2. Let me move this. Right. So for segment 2, we have for segment 2, we have the length of 125. All right, and then we have the elevation change of minus 8.5. Okay, and then remember we're still making use of schedule 40. Schedule 40, and then making use of 80. All right, and the last one is 100 meters, elevation change of 0.5, and then we view segments, and then we add 40, and then let's see. All right, so when we see this elevation change of negative, usually it's to determine like that's to say that there's a depression. You understand? When you talk about angle of elevation and depression, so when it's elevation, you have the positive. When it's depression, as it's going down, that is -8 as across the standard level. Imagine maybe the floor is straight, the ground which is following is straight, and then let's just assume that that straight line is 0. Then once we have an elevation, you have your negative, and then it increases. But once you go below that 0, you're going to negative. All right, that's just basically what it's all about. So we have the heat transfer information on the specified here. So we come to heat transfer. We're going to make use of estimate HTC. So let me bring this in back so that we see what we're working with. All right, so we have the temperature of the ambient, that's the ambient temperature of 5 degrees is determined to determine heat branch internal heat loss. All right, so let's do this. So we come here, ambient temperature of 5. All right, remember we said it was buried at a depth of 1 meter, so that's it here. Okay, and then we say when estimating heat transfer, they say all pipes are uninsulated, taking into account the pipe wall, inner and outer HTC. So we just said it's not insulated, so we're going to leave this, taking into account of pipe wall, inner HTC, and outer HTC. So with that, our branch 1 is complete, it's converged, and then we move on to branch 2. All right, so let's select our branch 2, another pipe, we add it. Okay. All right, so branch 2, let's do this. So that is gas well 2. This is B2 out. And then you see this is branch 2. All right. And then we see this is B2. Okay. 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 So another thing to notice, whenever you are putting in your streams, always remember to press enter. Whatever specification you put in, remember to press enter on your keys. All right. So let's append our segment. Let's add the segment. Let's go back to this. All right. So this is branch 2 we are working with. This is it here, and then we don't have any circles indicating that we have segments. So basically, we just have one segment here, and then we just append just one segment. All right, so let's look at what we have for branch 2. See, branch 2 just one segment, and then the length is 200 with elevation change of 23. All right, length 200 meters, elevation change of 23. All right, so we need to view our segments and add the necessary. All right, so let's come here, let's check this. So you see that this branch 2 is going to be at the diameter is 101.6. So let's go to still making the schedule 40 actually. So schedule 40. Okay, so let's add this. It was 100, so we look for this here. All right, so we're still going to be using the same specifications for the heat transfer. So estimate HTC 5 here, and then we have inner wall. All right, so this is working, it's converged. Let's see. So from this point, we need to, let's come here. All right, so after branch 1, we're done with branch 1, we're done with branch 2. So now they're meeting at the junction 1. This place here, this is where they're meeting. So we call that part junction 1 and mixing together. So we're going to be adding a mixer now, which represents our junction 1. All right, so change this to junction 1. All right, our inlet is B1 and B2, and the outlet is going to be J1, the junction 1 out. All right, with that is already solved. Now we move on to, okay, let's open this. So after we've connected these two together, the next thing is B4. Right, you see B4 is here, but let's work on B3. When we're done with B3, we connect B4 and then we join them together. All right, so let's quickly do that of B3 here. All right, so let's go B3, 5 segments. All right, so gas 3, V3 out. Remember, this is okay. And then we say this is B3Q. All right, so for this, we are going to be having, we have 3 segments to here. We have 3 segments, 1, 2, 3, with the first initial one. So let's go with, can check it from here. All right, so branch 3, we have 3 segments. All right, so let's go and append 3 segments, 1, 2, 3. All right, so let's start with the first one. We have a length of 160, and then let me quickly move this so that's okay. So we have a length of 160, and then elevation change for this is 12.5, and then let me do this. The second one is 100, and then the elevation change for the second one is minus 14. All right, and then the last one we have 205 as the length, and elevation change is minus 1. All right, so now let's bring this back in. All right, so going forward, let's check our diameter. All right, so for B3, we're still going to be making use of 76.2. That's the diameter. So for all of them here, so let's do that for B3. So view, schedule 40. All right, let's do for the next one. Schedule 40. All right, all right, so let's add these transfer. Okay, so it says that increment delta p is greater than 10%, as pressure drop. So we need to trace that. So usually whenever we're having things like this, it's usually from this sizing. So basically we have to increase one of the outlets. So let me just increase this to the next one. All right, so okay, all right, so now let's add, now we are done with branch 3. We are done with this branch here. So now we need to be looking at this branch 4. All right, so where it's now going to be connecting branch 3 and branch 4 at the junction 2. So let's add the branch 4. Branch 4 is coming here. Remember, it's after we've combined our gas 1 and gas 2 together. So J1 out, and then as before, Okay, so we take this as before Q. All right. So we append the segments is just one, and then all right. So let's see branch 4. Okay, branch 4. Length is 355, and then the elevation is -4. 355 -4. Okay, let's check the diameter. 101.6. So let's do that. I think our branch 4 is looking good. All right, so yeah, branch 4 is looking good. Let's change the name. Branch 4. All right. Okay, so now we need to join these two together, branch 4 and branch 3. So we just add the mixer here, and then we state this as junction 2. Sorry. Junction 2. Alright. In is before out and B3 out. We have G2 out. Alright, so that's okay, it's converged. Now we need to go to branch 4, okay, branch 5 and 6. Alright, so let's work with the fourth one, that's 4. So this one is just going to be having two segments. That's the initial segment and the second segment. So just two segments we're going to be having for this. All right, so let's see branch 6, two segments. All right, so let's do branch 6 before we go back to branch 5. No, you can actually do your branch 5 first, but let's do the branch 6 before we go to branch 5. All right, so give me a 5 in here. This is branch 6. As well, 4. Two segments. Right. 180 minus 5. we have 118. We have elevation of minus 7.5. We have 165 and elevation of minus 8. All right, so let's check the diameter. So branch 6 is diameter for branch 6 76.2, so that's 80. Let's get back to this. All right, so do the same for this too. All right, so working with 5. Okay, so I'm just going to increase this here to the next one. All right. Okay, so now we are going to be doing for branch, I think branch 5 here. So we need to append for branch 5. Put this here. So we have junction branch 5. G2 out. Energy strings B5Q. All right. Written, this is just one segment according to the diagram. So we just have just a single, there is no circle to represent another segment, just a single segment here. All right, so let's look at branch 5. Let's see 300 and then minus 16 as the elevation change. So the length is 300 and then minus 16 elevation change. Okay, so what's the diameter? Let's confirm that. For branch 5 we have 152, so what we just need to do is can double click on this actually, and then it should come up. Schedule 40, 152, so we look for like 150. Use 150. All right, so then estimate is 5. Okay, so I'm going to include pipe bore, include this and this. All right, so that's converged. So all we just need to do is to add another junction, which is going to be junction 3, connecting branch 5 and branch 6 together. All right, so when we do this branch 5 and then branch 6, and then call this is going to be junction 3, so J3 out, then we change the name to junction 3 here. All right, so that's converged, it's working. All right, so now the last thing to do is to add the final branch, which is branch 7. All right, so it's branch 7. All right, and then this is going to be J3 out. We have E7 out. Okay, and then this is going to be B7 Q. All right, that's for the energy stream. Let's quickly look at this. You can see that for B7, it's just a single segment which is sending into the gas plant. I can actually put gas plants here as the outlet. Let me just put two gas plants here. So let me change this to the gas plant. All right, that's better. So we just have a single segment. All right, let me close this one. Append segment. Let me check what's the length. 340 and minus 13. Okay, let's check the diameter. 152. Let's go to 40. So let's go for 150. All right, and then specify the estimates inside, and that's temperature is fine. All right, so just need to increase the pipe segments for the last one. And then the system should converge. Let's do that. Okay, let's increase this, and voila, the system is converged. So what it's just trying to let us know is that some of the parameters you'll be getting, that's the joy of this. Some of the parameters you'll be using lets you to understand that okay, there might be a problem here, so you have to increase the diameter of the pipe. That's what we've been doing since. So you have to increase the diameter of the pipe to accommodate that that pressure. You understand? So you don't have faults later on. So that's the idea of all this. So by this, we've been able to create a gas gathering system from different wells. All right, need to create a gas gathering system from different wells. This one. All right, so just like what we have in the topographic graph, we have from gas as well 1, well 2, it's going through branch 1 and branch 2, and then the branch 1 has 3 segments which is specified. Branch 2 has just a single segment. We got them together at junction 1, and then 2 of them went together, that's combined gases. Now they are moving at branch 4, going through branch 4, and then for gas well 3, which is passing through branch 3, having a pipe segment of 2. I think we confirm that. Okay, it has three segments. It has 3 segments. All right, so having 3 segments in the pipe, moving to combine with to mix with the B4 out as gas well 1 and gas well 2, and then so it mixes with the gas from here, and then it goes to branch 5, and then coming down to junction 3 where it mixes with the gas from well 4, and then passes through another pipe. Gas well 4 passes through a pipe. It's 2 segments, and then moves to junction 3, which is this junction here. That's the junction 3. And from junction 3 passes to another pipe, which is branch 7 going to the gas plant. All right, so that is it for gas gathering. All right, see you on the next video. Thank you.